Hey, what's going on, guys? Comic Games here. Here is yet another development progress video on building 6502 processor simulator in x86 assembly language. And well, I didn't yet do that much, and currently the only instruction I have implemented is LDA, which stands for load value to accumulator, and only processing the immediate addressing mode. So currently I have this only immediate addressing. So what has changed since the last video? Well, I've added more debugging routines, and also now I have a test program down below here. So these are the 6502 opcodes. So A9 stands for load to A register in the immediate mode, and then the next byte is what kind of value do I want to load in particular. And what I need to bear in mind here as well is the flags that gets altered. So before I start the demonstration, just a few words on how do I verify myself, basically. So here is the Lda instruction. Here is the A9 opcode here. So this is the only one being processed for now, and then followed by the value, right? So it affects the negative and the zero flags. So negative flags gets affected every time when the most significant bit is set to 1 or true. So in this case, negative flag is set, and the zero flag is set in case if we load the value of 0 into the A register, no matter if it was 0 already, or it wasn't. So if we just load the 0 value, the zero flag gets affected. So here I'm referencing the JavaScript simulator, 6502 simulator, adopted by Nick Morgan, and it's very nice in terms of, if I just say, let's say LDA, and let's say the value of hexadecimal 12, and assemble and run. So here it sets, it's what it does literally. So it sets A register to 12, right? Then the program counter gets incremented by, well, actually it currently shows where it points to. So this is kind of like yeah, just where it points to. Yeah, I just realized that in my case it works. I mean, it probably works the same, but the debugging stuff is being printed a little bit different. But no, it doesn't matter at the moment. So now the flags. So let's say if I load the value of 0, then here the zero flag would be able to 1, right? And if I load whatever value that would have the most significant bit being set, so by saying the most significant bit, so this might be like this, for instance, like this, what else? Like this, and so on. So if it starts with 8, right? So 80 in this case, and hexadecimal. So the binary on the left, hexadecimal on the right. So this is A0. This is E0, right? This is F0, right? Oh, I'm sorry, not the plus. So every time this flag is being set, the negative flag gets affected and becomes 1. So no longer being 0, but starts being 1. All right. Yeah, and here we have all the flags in binary, and by the way, so it's up to 8 bits. So I have a single byte to represent this processor flags, and I just perform bitwise OR on using the specific mask if I need to kind of turn on the either the 0 flag or the negative flag. So here, for instance, if one of this value, like 80 for instance, and assemble and run, and here we have the negative flag being affected, or the same with, say, A, assemble, run, same thing, right? Same with E, assemble, run, and so on, right? So, well, with the load instruction, they can't be set both, because if at least one bit is set, like this negative bit, then it's not a 0, right? So only one of these flags gets affected. So and another little thing, so a hex dump here, so just to verify that the opcode is really A9. Well, even though I've grabbed the opcodes from a project by Dave Poo, where the guy is writing the same similar thing but in C++, so I have the opcodes for all the possible operations, for all the addressing modes. I just grab those opcodes, so they are available here, so I can just compare with these sort of values. But am I really doing that? Execute immediate, nope. Yeah, I do it here. So yeah, let's just have a look how the output works, and then probably we can walk through the code a little bit. So yeah, I've added really lots of debugging things here. So, well, without further ado, let's actually have a look. So by default, it prints. So let's actually start referencing the code. So what I'm doing by default, I reset the CPU, which means I set all the register values to the default values. The program currently leaves at, well, the absolute address is E600 in hexadecimal. The local offset from the perspective of the emulated or simulated memory is 600 FF. I didn't yet specify it here, so this is the RAM. So this E00 is just the offset to add in order to get the absolute address where the program lives. But relatively from this simulated RAM, it's located at 600, just like it's done here. Well, I know probably not the best ever way of doing things, and not the real place where the program would occur. But anyway, that's just a temporary thing. So maybe I will make it a bit more like look like something real in future. But for now, it's fairly enough just to have the program, the 6502 machine code somewhere to fetch them from there to verify the instruction. And once the instruction is verified, then processing the rest of bytes which serves as an argument, and then just trying to execute the instruction. That's pretty much all about it. So by default, what I do, I print the starting address where my program is located. So this kind of test program I have down below in my CPU file. So where is this? Yeah, here is my test program. So A9, which stands for LDA immediate data 00, A9 F2, A9 E3, A9 37 hexadecimal. And here I have all this, like A9 are the opcodes, and the byte next is the value, right? So I did initialize this. How did I do that? So just I have created this load program routine here, which actually does take the input. So load program, it just points DI to the program, which is E600 hexadecimal, and then it points SI to this program here, to the test program, right? And I'm just wondering, where did I point SI? Yeah, SI points to the test program, right? And then we just load in the byte from the test program. If it's so, FF currently is the temporary value for like end of input, because if this is 0, then if we have a 0 input, it just breaks and doesn't load anything else, which is weird. So just the temporary constant to make sure that we have exhausted the bytes of the input program. And in this case, we just drop back from the return from the function. Otherwise, we store a single byte to where DI is pointing to, and DI is pointing to this E600 hexadecimal, where the program leaves in the territory of the simulated random access memory for 6502 processor. All right, so then what happens next is, so I just print the range, just so SI. So I have this print memory range function, which so SI serves as the starting point word to look for memory, and DI serves as the endpoint. So program plus little offset just to see a few lines, so a few bytes. So one line would be enough, but just to give you an idea. So we have the addresses where we're printing the memory. So it's like a hex viewer basically. So really lots of debugging stuff being done here, right? And then after we have AX, Y register, program flags, stack pointer, and program counter at their initial values. So after being reset, this is how they look. So again, a program counter is temporarily points to the 600s hexadecimal within the simulator RAM. Now, what the flag means, so this should be treated as the binary, not as the hexadecimal. So for instance, so just make this always on top, and here, so this is going to be 0, 0, 1, 0, 0, 0, 0. So this is how the flag map looks like, and here we have the negative, overflow, reserved, binary decimal, I guess. I have them somewhere. Hold on, guys. I just have them, this flag somewhere. Here they are. So just grab them quickly. All right. So, and yeah. So only this reserved flag is set to 1, the rest of flags are set to 0, right? And the next, so now it's kind of in a break mode. So I kind of like mimic a breakpoint every instruction. So every next instruction I have a sort of a breakpoint. So how do I implement that? You might be wondering. So here in the execute function, so I'm pointing aside to the program, reserving DS to later on be able to hook the local variables. That's a very clear thing. Then loading the single byte. So here, literally we're loading the opcode, and then so here would be a giant kind of like switch case statement equivalent. So would be comparing the whatever we have in AL after load single byte with the set of predefined opcodes. It's around 150 with all the opcodes with all the addressing modes. And then if it hits the certain given opcode, it just jumps to the certain kind of label. So here LDA immediate. So here is the LDA immediate. So LDA instruction with the immediate data. So that's what the A9. This constant is just A9. So this is what A9 is kind of corresponds to. So we go here. Then this load single byte loads the value that we want to put into the LA and into the A register. Then we restore in the data segment to hook the local variables, as has been mentioned before. Then I increment program counter by 2 because so it has to point to. So first initially was pointing to the very first opcode, right? And then it needs to skip 1 byte, which is the opcode, and then he needs to skip another byte, which is the value. And I'm just holding a second, guys. I just want to make sure it just points to the program, and program is E600s, should be E600s, which it is. Okay. So yeah. Then here, this line actually initializes the A register with whatever we have in AL, which holds our value to load into the A register, right? Then these two lines serving the purpose of setting up the flags properly. So if AL holds the 0 value, we need to set the 0 flag. And this is the mask. So 800 hexadecimal in binary is 1000 and 4 zeros. So we're testing this bit if it's equal to true. In this case, we also want to set the negative flag. And both the 0 and negative flags been set here. So I've So actually here is the label, and the label calls set 0 or set negative, because of the fact that we would be setting this flag from various instructions. I decided to separate them as kind of single functions. So we just call return and we're done. After we're done, we just go into Lda immediate next here, and then we go into execute debug. And here this call break actually allows me to so before every instruction is kind of executed, or better to say after the instruction is executed, I just pause the execution, right, and then I can resume it. So here in this case, so just to give you an idea, so the very first value we load is 0, 0. So A register should be still 0. However, the 0 flag should get affected, and after, so 0 flag is this one, so this would be 2, so this would be 22 hexadecimal. So after I hit enter, I'm sorry, not there, here. So after I hit enter, you see like flags has changed. So now this flag, the 0 flag has been set to 1, hence this value 22 hexadecimal. Right, so then we're gonna be loading F2 to the A flag, and I press any key, and we get it. Okay, and then also negative flag has been affected because F actually has the most significant bit being equal to 1, hence we kind of like bitwise or that bit with the program flag. So now it's not 22 but A2, so it's so in decimal this is going to be 10100010, right? So it gets affected as well, and also by the time this is happening, the program counter gets incremented as well. I just figured out that apparently I'm not sure, is this really the same how it works in this online JavaScript emulator? So if I say LDA, for instance, here, just want to make the same, so say F2, LDA, and say E3, and hexadecimals, all the hexadecimals. Oh, sorry, already were there, okay. So LDA and 37. So assemble, and if I just use the debugger, so yeah, this is kind of it. So after the first, say like the negative flag, or hold on a sec. Oh, this is just, yeah, I should make it like this. So assemble, no, assemble, reset. One more time. So debugger, step. Yeah, so this is the same. So we have this, well, it also has this binary decimal, no, it's not a binary decimal, it's a break flag. I don't have this, but it doesn't matter at the moment. So again, where is the camera, right? So, yeah, like this. So 602, right? The next step, 604. The same that we got here, right? What else? So it gets affected, it gets the negative flag being affected, then E3, now it's equal to E3, and finally 37, so 37. So here, okay, so just loaded A2, no, E3, yeah, E3, and then loaded 37, and we are done here. So still the flags has just remained the same. Here is the instruction pointer. Well, here, well, for some reason it just, I don't know why it prints 9 here already. Was gonna, so if I just break here, it's just a matter of the way how to, 1, 2, 3, 4. Yeah, it's like, it just here it just points to the next instruction. That's pretty much all about it. So yeah, I think this can be thought as the same now. So we have just executed for up to 4 instructions. All the instructions represent this LDA. So this is kind of the code that we've just kind of like executed on our Bootable 6502 processor simulator. But we have been using this hexadecimal values, obviously. And you see, like this hex dump that we have in the JavaScript version, I'm trying to mimic this, but again, like, the difference is that this is just a hex dump for assembled code, and this is actually the hex dump what happens in the memory. So if you want to see the equivalent here, we just need to go to the monitor and starting from the 600s and then just assemble, run, and here see, like, we have this and the same here, but it just takes, I think, 1, 2, 3, 4, 8, 16 in a row, but here we only have 8 because of the 40 by 25 characters video mode, which I'm taken from Apple One. I'm inspired by Apple One computer, hence the how all this sort of a thing looks like. So yeah, a bit of an inspiration from Apple One is on the cards here. Okay, and what else to demonstrate? So if I just disable this debugging stuff, so if I don't call break, in this case, you see, like, it just runs, and it prints only the initial. It only prints the initial debugging stuff here. So if I want to print the debugging stuff after the execution, I can do this like so, and in this case I just have the very last value that we did put into a register. The flag's already been affected, the program counter has been affected as well. So this is pretty much all about it, right? But again, like, it's really handy to see what happens during the execution using this kind of like break emulation, simulation, call it however you want. Okay guys, so I think this is it from my side. This is very tedious to do, not boring, but tedious, I would say. And from now on, in order to come up with the full-blown kind of like simulator, I just need to handle every little instruction, and it really takes time and effort, to be honest, because all of this debugging stuff is really a bit overwhelming, to say the least. So yeah, it's only the immediate mode, the immediate addressing mode, and for instance, say for LDA, we have the 0 page mode, 0 page with X offset, absolute X, Y, indirect X, Y, and all of these different addressing modes. So in order to handle the single instruction, it really takes lots of time and effort to complete. So to be honest, I feel a little bit overwhelmed, and yeah, I don't know if I actually managed to bring all this stuff together and to make it work eventually, but it's very rewarding, I believe, because it's gonna be so cool being able to actually make it like people did on Apple One back in 1976, like just typing in 6502 machine codes and making computer do whatever they ask him to do, including loading the files from cassettes. What else? Yeah, and then actually they could load basic assembly or some games to play, whatever. So this is really fun, I believe, especially bearing in mind this is bootable, and it looks really awesome when it runs on the real hardware as well. So yeah, we'll see how the project goes, and when I have something interesting to share with you guys, I will make another video and I will make another development progress video to showcase where I would be at that point. So yeah, this is it from my side. Thanks for watching. Until the next time, and take care.